Hi, in this video I'm looking at sketching the locus of a complex number for some sort of equation such as this, where I've got z minus 3 is greater than z plus 2 minus I. So we want to know, how would I draw, where is this complex number z located, or where could it possibly be located? What's its locus? So what's its path that it can sketch out, so that it's always following this rule here, that this side must be bigger than this side. So let's have a look at what all of this means. So if we start thinking about having complex numbers, so let's say I've got one complex number here, which we'll call z1, and I've got another complex number somewhere else in the complex plane, z2. Then I can have our complex number z that we care about as a third point. And this point is mobile because z can be defined as any x, y, I location on the complex plane. Now, if we've got three complex numbers, then these basically make up a triangle. So I can have the line that joins z1 to z, and the line that joins z2 to z, and we've even got a line that joins the two together, and we have a triangle. But what does this triangle really mean? So if we consider simplifying our situation, so let's consider the equation z minus z1 equals z minus z2. Now, if we think about what the left-hand side of this means, the left-hand side of this is basically the distance between z and z1. So z minus z1 is the difference between the two complex numbers, and then by taking the magnitude of that, the absolute value, we get it strictly just down to the distance because we take away the direction aspect. And if we have a look at the same for the other side, it's going to mean the same thing. It's the distance between z and z2. So if we have this equation here, it means that the distance between z and z1 must be the same as the distance between z and z2. So if we go and take that back to our triangle here, that means that this line here is the same length as this line here. These two are the same length. Now, if we extend this back to our situation where we've got z being defined by this rule here, where these two distances must be the same, but z can move however it feels like. It is defined as any locus point on the complex plane. But it must also follow this constraint that the distance between the other 2 points must be the same. So if z wants to move, it could say move to here, because then these two lines would be the same. It could move up here, because then these two lines would be the same. It could move all the way down here, because these two lines could be the same. And that's really the only places it can move. And if we look at the result of this, we actually end up with a straight line. If I can draw a straight line running through here. And if I drew my straight line and all my other points properly, then this line would actually be perpendicular to the line joining z1 and z2. It would actually be at right angles. And that's what this equation means. That's what it all comes down to. So that gives us our definition. The locus of z is the perpendicular bisector of the line through z and z1. So it is the line that z can follow, and it's always got to be perpendicular to this line that joins z to z1. So that's the definition of the locus for this equation. Now, if we extend that out to where we have this, where we've got an inequality, that means that the locus is no longer restricted just to this line. It's restricted to an area where one distance is greater than or less than the other distance. So if we have a look at that problem, so let's actually have a look at that problem. So let's go back to our equation. So we had z minus 3 is greater than z plus 2 minus I. So if I think about first these points, well, let's put this in terms of the fact that we need z minus z1 and z minus z2. So I've got that one here. I've got z minus positive 3, and that's going to be greater than z minus negative 2 plus I. I've just factorized out a negative so that I have z minus my complex number point. And then if we think about actually having these as points, this one here, well, it's completely real. So its real component is 3 and its imaginary component is 0. So it's basically the point 3, 0. And this point over here would be, well, it's got a real component of negative 2 and an imaginary component of 1. So it would be the point on the complex plane negative 2, 1. So now if we get up a grid and we actually look at graphing these points, so if I make up some axes on my grid, so let's grab some axes. So if this is the real of z or x, and if this is the imaginary of z or yi axis, then we can plot our 2 points. So I've got our first point, 3, 0 here, which we can say put over here. It can be the point 3, 0. And we've got our other complex number, negative 2, positive 1, which we'll put here. So we can have negative 2, 1. And we can join them together so we can show what the line joining these two together is. We can then draw in the perpendicular bisector. So let's go and draw in our perpendicular bisector. So that will give us a line that is halfway between these two. It should be about this point there. And at right angles to it. So to be coming up at about that angle there. So but we're strictly greater than, so I can't draw it as a solid line, so I've got to have it as a dotted line. See if I can make that a little bit more perpendicular. And we'll come down here. So that's our perpendicular bisector, so that's the middle point. So z, our complex number, has to be on one side of this line or the other. And it's going to be a shaded region. So we're going to need to shade the correct side of this line. Now, if we look at our equation, it says the distance to this point must be bigger, this is greater than, the distance to this point. So if I'm on this line, my distances are the same, I want to be further away from this point, the 3, 0 point, than I am from the negative 2, 1 point. So that means I need to be on this side of the line. Because if I'm over here, then I am further away from this point than I am from this point. If I'm here, say, I'm really close to this point and I'm quite far away. If I'm over here, I'm a fair distance from here, but I'm even further from this point. So this entire region is what defines where z could be. And we label it as a dot, z, x, y, and we color in the region. So this entire region now defines the locus of z. Before, where we had our little diagram, if there was some sort of Cartesian plane here, then this line would define the locus of z. So the locus of a complex number can be defined as a region or as a line. We can even get a situation where it's defined as the region and a line. So if we get another equation up, So in this case, we're going to have z plus I is going to be greater than or equal to z plus 2 minus 3I. So let's first write this as z minus I. So we got z minus z1, so we got z minus negative I is going to be greater than or equal to z minus negative 2 plus 3I. So now we're in terms of z minus z1 and z minus z2. So now let's put on our axes. So we can have my real axis here. Oh, sorry, my imaginary axis there, and my real axis, let's put that here. So we can have, well, this is x and this is yi. So we can have our first point, which is going to be this one here, which has got no real and a -1 imaginary. So it can be the point, say, down here of 0, -1. And we can have our other point, which is -2 real and +3 imaginary. So -2 real, +3 imaginary will say be somewhere up here. We can put in the line joining these two as a bit of a sketch, and then we can put in our bisector, our perpendicular bisector. So halfway it's going to be about here, and because we're greater than or equal to, we're going to have a solid perpendicular line. So we'll put in a solid perpendicular line, and then we just need to work out which side is going to be our region. So this says that our distance to this line this point must be bigger than our distance to this point. So that means that we must always be further away from this point down here, because that's our 0, -1 point, which again means that we're on this side. So our z of xy can be any point on this line or this upper region from the line. Okay, so that is the definition of a locus of a complex number where we've got 2 points involved. So we could either be equal to, where it's a line, we can be greater than or less than, where it's a region on one side of that line, or we can be greater than or equal to or less than or equal to, which means that we're a region and the line. And we just got to work out where's our perpendicular bisector of the line joining our two complex numbers, and then which side of the line is required.